The fundamental principle of counting, also called the rule of product, says that if you have a sequence of choices, and each choice can be made in a certain number of ways, the total number of possible outcomes is the product of those numbers. For example, if you pick a shirt 3 choices, and then a pair of pants 4 choices, you have 3 times 4 equals 12 outfits. In mathematics, we often write this product using factorial notation. The factorial of a non-negative integer n written n factorial means the product of all positive integers up to n. N factorial equals n times n minus 1 times ... times 2 times 1. It arises naturally when we count the number of ways to arrange n distinct objects of permutation. For instance, arranging 5 books on a shelf can be done in 5 factorial equals 120 different orders. Explanation: a permutation is an ordering of objects. When all objects are different, the number of permutations of n objects is n factorial. When some objects are identical, we must correct for overcounting because swapping 2 identical objects does not create a new arrangement. The formula becomes n factorial over n sub 1 factorial times n sub 2 factorial, and so on, where n sub I is the count of each type of repeated object. Example: arrange the letters of a B. There are 3 letters total, so 3 factorial equals 6 naive permutations. However, the 2 A's are indistinguishable, so we divide by 2 factorial equals 2. Hence, the distinct arrangements are 3 factorial over 2 factorial equals 3, a B, a B, a B, a A. A real-world analogy is seating 3 people where 2 are twins. Swapping the twins does not change the seating picture, so we count fewer distinct seatings. A combination chooses a subset of objects without regard to order. The number of ways to pick R objects from n distinct objects is written n choose R and computed as n choose R equals n factorial divided by R factorial times n minus R factorial. Think of a lottery where you must select 3 numbers out of 7 possible numbers. The order you write them does not matter, so the count is 7 choose 3 equals 7 factorial divided by 3 factorial times 4 factorial equals 35. Another everyday picture. A pizza place offers 7 toppings and you want any 3 of them on your pizza. The number of topping combos is the same binomial coefficient. This formula also appears as the coefficients in the expansion of x plus y to the n. The binomial theorem describes how to expand a power of a sum. X plus y to the n equals sum from k equals 0 to n of n choose kx to the n minus ky to the k. The term n choose k tells us how many ways to choose k copies of y, and consequently n minus k copies of x from the n factors. To derive the general term, imagine multiplying n copies of x plus y. Each factor contributes either an x or a y. To obtain a term with exactly k y's, we must pick y from exactly k of the n factors and x from the remaining n minus k factors. The number of ways to decide which k factors give y is the combination n choose k. Therefore, the kth term starting at k equals 0 is n choose kx to the n minus ky to the k. Explanation: using the binomial theorem, we can write out concrete expansions. For n equals 4 open parenthesis x plus y close parenthesis to the 4th equals binomial coefficient 4 choose 0, x to the 4th plus binomial coefficient 4 choose 1 x cubed y plus binomial coefficient 4 choose 2 x squared y squared plus binomial coefficient 4 choose 3 x y cubed plus binomial coefficient 4 choose 4 y to the 4th equals x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. For n equals 5 open parenthesis x plus y close parenthesis to the 5th equals x to the 5th plus 5x to the 4th y plus 10x cubed y squared plus 10x squared y cubed plus 5xy to the 4th plus y to the 5th. For n equals 6 open parenthesis x plus y close parenthesis to the 6th equals x to the 6th plus 6x to the 5th y plus 15x to the 4th y squared plus 20x cubed y cubed plus 15x squared y to the 4th plus 6xy to the 5th plus y to the 6th. These numbers 1, 4, 6, 4, 1, etc. are exactly the entries of Pascal's triangle for rows 4, 5, 6, showing the direct link between the theorem and the triangle. Explanation: to find a specific coefficient, locate the term that matches the exponents you need. In open parenthesis x plus y close parenthesis raised to the fifth power, the general term is 5 choose k x to the power 5 minus k times y to the k. We want the term x cubed y squared. Set 5 minus k equals 3, so k equals 2. Then the coefficient is 5 choose 2 equals 10. Thus the term is 10x cubed y squared. In practice, you can think of it as how many ways can we pick 2 y's out of 5 places. There are 10 ways, giving the coefficient. This method works for any power and any pair of exponents, as only the sum of the exponents equals the overall power n. Pascal's triangle is built by starting with a 1 at the top. Each subsequent row begins and ends with 1, and every interior entry is the sum of the two numbers directly above it. Row 0, 1s. Row 1, 1 1s. Row 2, 1 2 1s. Row 3, 1 3 3 1, and so on. The nth row starting with n equals 0 contains the binomial coefficients n choose 0, n choose 1 up to n choose n. Therefore, Pascal's triangle gives the coefficients for x plus y to the n instantly. For example, the fifth row 1 5 10 10 5 1 tells us the coefficients in x plus y to the 5. The triangle also helps with combinatorial identities such as n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k, which is precisely the rule used to build the triangle. Explanation: exam-style problems often combine counting ideas with the binomial theorem. Example 1, a committee of 4 people is to be chosen from 6 men and 5 women. How many committees contain exactly 2 women? Solution: choose 2 women from 5, 5 choose 2 equals 10, and 2 men from 6, 6 choose 2 equals 15. Multiply because the choices are independent. 10 times 15 equals 150 committees. Example 2, using the theorem. Find the sum of the coefficients in the expansion of 2x minus 3 to the 7th power. Set x equals 1. 2 times 1 minus 3 to the 7th power equals negative 1 to the 7th power equals negative 1. The sum of coefficients equals the value of the polynomial at x equals 1, so the answer is negative 1. Example 3, identity. Prove sum from k equals 0 to n of n choose k equals 2 to the n. This follows from the binomial expansion of 1 plus 1 to the n equals 2 to the n, where each term n choose k appears. These types of problems test understanding of counting, factorials, combinations, and the ability to translate a word problem into a combinatorial expression.